So today you're going to use the SSS, SAS, ASA postulates, or the angle side or hypotenuse leg theorem, just to show that two triangles are congruent. Last week we talked about the CPC-TC, and we used that to show that matching parts of congruent triangles, but how do we know if two triangles are congruent in the first place? So until now, we could prove triangles are congruent by only showing all sides are congruent and all angles are congruent. So if this side equals this side, and the other side equals the other side, and the side equals the other side, and that angle equals this angle, if you knew everything about the sides and angles, if you knew that every side was congruent to another side and every angle was congruent to another angle, then they had to be congruent by the CPC-TC. But there's theorems out there where you don't have to know everything about the triangle. And so the first one, and I don't know if we're going to fill it in exactly, but this one says, if you know, and this is called the side, if you know this side equals this side, so if you know two sides are congruent, and then you know these two sides are congruent, and then you know that this side is congruent to this side, then that's also enough to know the angles are congruent. So therefore, the triangles are congruent. We call this the side postulate. And we say if three sides of one triangle are congruent to three sides of another triangle, then that's enough to show that the two triangles are congruent. So now let's look at this diagram, and we're going to determine, does the triangle XWY, so XWY, the triangle on the left, is that congruent, that's what that symbol means, congruent to ZWY. ZWY. In other words, does this triangle, is it the same size and shape as this triangle? And can we prove it by SSS? So the first thing they tell me is that, they tell me right here that this side equals this side. And then they also tell me that y is in the middle of x and z. They say that right here. They say y is in the middle of x and z. Well, if y is in the middle, by definition, being in the middle means that they are congruent, because y is the midpoint. So now we have sides, and do we know that the other side is congruent? Do I know that this side right here is congruent? And the answer is yes, because if they share the same side, then those sides have to be congruent. So yes, we could call this by the SSS. And we use the word reflexive property that says that if they share the same side, then the side has to be congruent. So yes, we do have enough information. So do we have enough information? Yes. The orange equals the orange, the green equals the green, and then the pink is going to be the same because it's the same side. Another theorem, and it's called the side angle side. If you know, and I'm just going to pick a random side, if you know that a side equals a side, and you know a side equals a side, and then you also know about the angle, and it has to be the angle in the middle of the two sides. So notice like this angle is not in the middle of the two sides. This angle is not in the middle of the two sides. But if I know that this angle, we call that the included angle. If this angle equals this angle, then this is what we call the side angle side. So we have side, angle, side. Side, angle, side. So you could use the side angle side postulate to prove two triangles are congruent. So if you only know two sides and the angle in between, you could prove congruency. So to fill this in, if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the triangles are congruent. It is very important on SAS that the angle be in between the two sides. So if I knew this angle, you can't use SAS. If I knew this angle, I cannot use SAS. It has to be the angle that's included between the two sides. So here's an example. Do we have enough information to show that this triangle is congruent to this triangle by the SAS? Well, we know that this side equals this side, and by their markings. We know that this side equals this side. So can I use SAS? And the answer is no. I cannot use SAS because it would need to be the angle in between the two sides. So this angle would need to be here, this angle would need to be here. Okay, so because the included angle is not congruent, that's not enough information. So I would say no. It's actually angle side side, angle side side, which is not a congruence theorem. Alright, let's look at this one. The two triangles can be proved congruent. State which two triangles are congruent. That's obvious, there's only two triangles. And the reason why. So, how do I know these are congruent? I know that this side equals this side. I know that this side equals this side. And all we've learned so far is SSS and SAS. Now there's no way to know that this equals this. But because these are parallel lines, remember when we did two parallel lines cut by a transversal? And I know it's been a while, but when you have two parallel lines cut by a transversal, then we know that this angle equals that angle. And we call those alternate interior. And it might help to draw this out. Like, remember when we had parallel and parallel, and then we had the transversal? We would call this angle and this angle alternate interior. Do you remember that? And so because these lines are parallel, we know that this angle equals this angle. So then, yes, I could prove they're congruent by SAS. Side, side, the angle in between, side, side, angle in between. Now remember, when you're saying triangles are congruent, you have to go in the same way. So if I start with W, I need to start with T. And then it goes W to X, so I need to go T to X. And then the other one would be Z. The next theorem is called an angle side angle. So if you know, say this angle equals this angle. And then you know that it has to be this side or this side. I'll go with this side. Let's say you know this side equals this side. And you know that this angle equals this angle. Now notice in this one the side has to be included in between the two angles. So if you have the two angles are congruent and the side in between those two angles, then you can use what's called the ASA. So if two sides, if two angles, angle, 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 and the included side of one triangle are congruent, the two angles and the included side of another triangle, then the triangles are congruent. So if you have ASA congruent to ASA, you can use ASA. So an example, can you determine that the two triangles are congruent by ASA? So let's look. We know that this angle equals this angle. So there's one of our angles. And then they also say that this angle is 90 and that angle is 90, so that'd be another angle. And we could use ASA if the side is in between those two angles, and it is. So because the side is between those two angles, we call that an included side, we could use ASA. So the answer would be yes. Now how would you name it? You would say triangle. And it's your choice where you want to start. I'll just go in alphabetical order. RST is congruent. So I have to start at the same place. So I have to start at the right angle. So I'm going to start at P. And then went R to S. So I'm going to go P to O because S and O. And then I would go the T, the orange one, so I need to go to the N. You just have to go in the same order. And last week we learned that this means R is congruent to P, angle S is congruent to angle O, angle T is congruent to angle N, by looking at this. So can you determine if these two triangles are congruent? Here we have angle and an angle with the side included, so this one would be ASA, but here we have angle, angle, and the side isn't included, so we cannot prove that they're congruent. They might be congruent, we don't know, but we don't have enough information to prove, so I would say no. So the question is, does the side always have to be between the angles? And you could probably guess. The next one's angle, angle, side. So if you know an angle is congruent to an angle, and then you know another angle is congruent to another angle, and then you know a side is congruent to a side, notice it is not included, then we can use the angle, angle, side. Okay. So if two angles and a non-included side, of one triangle are congruent to two angles and a non-included side of another triangle, then that's enough to show they're congruent. So if this side had been between the two angles, like if it had been here and here, we would call that ASA. If the side is not included, we call it by angle side. So it could have also been over here. So if the side's included, you say ASA. If it's not included, then you say AAS. Right. Well, can you show the two triangles are congruent by angle side? Well, I have an angle congruent to another angle. I have an angle congruent to another angle, so that takes care of the two A's. And then remember, to be angle side, you would know that one side equals another side that's not included. And so I know, because they share the same side, that so I have angle side, angle side. So the side is not included between the two angles, but we know it's congruent because they share the same side. So by the reflexive property, this side equals this side is the same thing. So this would be angle side. So I would say yes. And then I'm not going to name these congruent triangles because they left off some letters there, so it's going to be hard to name this triangle. Now, angle side, A, if you look at the first, it does not work, and not just because it spells a bad word. So ASS does not work. Most math teachers call it SSA. SSA is not enough information. And if you look it up, it's also called the Hl Theorem. Alright, next. This is only true for right angles. If you know, and remember, to be a right triangle, you have to have 90 degrees. So this only works, you can only use the hypotenuse leg if it's a right triangle. So if you have a right triangle, and you know the hypotenuse equals hypotenuse, this is called a hypotenuse in case you forgot. Remember, the hypotenuse is always along the side. It's always across from the 90 degrees. So if you know the hypotenuse is congruent to the hypotenuse, and then you know a side, or we call these legs in right triangles. If you know that a leg equals the other leg, either leg, it doesn't matter, then that's enough to show they're congruent. If you have two legs, that's not enough. It has to be a hypotenuse and a leg. Okay? So I'll fill in this in. If the hypotenuse and the leg, notice you only need to know one leg, of a right triangle are congruent to the hypotenuse and a leg of a second right triangle, then the two triangles are congruent by the Hl theorem. Remember, HL only works if you have a right triangle. So all you need to know is two pieces of information. The hypotenuses are congruent, the legs are congruent. So here's an example. Can you use HL? The answer is no. There is no right angles anywhere. You cannot use HL unless there's a right angle. So this would be no, that's easy. Can you use HL on this? Well, possibly. Do I know? So it would be across from the 90 degrees, the hypotenuse. Do I know that this side is equal to the other side? Do I know that this top of this triangle is equal to the bottom of this triangle, which would be the hypotenuse? Yes. This is the hypotenuse. So there goes my H. And then do I know a leg is congruent to another leg? Yes. So then I would say yes by HL.